Yeah, so we're going to talk a little bit about who are we. So who's Insight Analytical? What do we do? What do we bring to this industry? And then we're going to talk about the Barben auction analyzers. And Barben is, you'll see it, I think their logo is on a bunch of the other slides. Barben's an Amatech company, and makes a rather unique auction analyzer that we've found very useful in a certain set of applications. And so we'll talk about applications, why we use it, what advantages it brings. As far as Insight is a Calgary-based systems integrator and distributor. Our shop is in the northeast of Calgary. We co-locate with the local Swagelok distributorship. Leaves us a very large manufacturing floor available. We have about 20,000 square feet of accessible manufacturing space, lots of big doors, big 10-ton overhead crane. We can bring a full analyzer building in. We are AB 83 compliant fabricator. So for the Canadians here, AB 83 is important because it means that we can manufacture systems that meet the required pressure vessel codes for installation and process applications. It's a specific set of regulations, kind of similar to the European pressure equipment directive. But we've done projects with CRN for Alberta, British Columbia, Ontario, and Saskatchewan. A lot of the people that are here are people that have worked with it at other companies. We bring a lot of history, even though Insight's been around, only been around since kind of around the start of 2016, late 2015. A lot of us have worked together for 10, 20, 30 years. And so we've got a really strong team with good documentation resources, drafting and design, engineering design resources. Journeyman electrician, journeyman instrument people on staff, full factory acceptance test here in Calgary. From the systems integration side, we will work on projects kind of that no project too big or too small. We'll do things from just custom sample systems through full process analyzer integration. We'll add in any necessary PLCs and automations that we need to do for it. We will do full analyzer buildings and shelters. We'll work on projects right from the front-end engineering design side of things. So helping to specify the appropriate analyzers for a given application through to detail engineering and design and fabrication. So we'll build everything here in Calgary. So integrate an entire system here in Calgary. Do full field commissioning. And of course, we try to service all the product that we sell. Some of you may know me from teaching other sample system courses. I used to teach courses internationally on designing analyzer sample systems. It's one of the things that we like to believe we excel at is trying to put the right sample system in for the right application. So the product that we're going to talk about mostly today is the Barben OXYvisor. This is there used to be the Barben 4401. The OXYvisor came out a couple of years ago. Very nicely engineered packaged product, nice little touchscreen display on it, which is great in an explosion-proof device. It's got some great features, and so we're going to talk a little bit about the analyzer, how it works, and then some of the applications that we use it in. So initially, I'm going to talk a little bit about why do we even bother? I always tell people nobody puts analyzers in because they really like them. They're expensive, they take maintenance, and so we have to always understand, well, why do I really want to make this measurement? And so, with oxygen, it's one of the most ubiquitous measurements we have. We see it in almost every industry. Oxygen can be extremely corrosive. So in things like boiler feed waters, it can be very corrosive. It can, in pipelines, it can cause corrosion or contribute to corrosion in pipelines. And so it can attack our customers' assets, whether it's piping, metallurgy. It can cause corrosion issues in gas phase, liquid phase, or steam type applications. It's also important from a process efficiencies perspective. If we get oxygen into certain operating vessels, like for example, amine units where we're doing H2S and CO2 removal, the oxygen can contribute again to corrosion and the formation of things like heat stable salts that affect affect facilities operations. And it's also important for its ability to attack and damage catalysts. And so it can be important when we're looking at product quality, like things like methanol and ethanol production. And finally, there's the safety related issues. Oxygen ingress into a stream that has hydrocarbons can lead us to having a flammable or combustible mixture. So we want to be sure that, say, for example, if we're doing compression at a VRU, that we don't have leaks in the compressor and we're not getting oxygen into the vapor recovery unit streams and making a potentially combustible mixture that way. So, from this perspective, we'll often see it in gas phase applications on things like vapor recovery units, flares, etc. So the Barben oxygen analyzer, the guy that we're showing up here, is an interesting device. Again, my background, I'm a spectroscopist by trade. So a lot of the products that Insight has come to be selling are often based somehow on spectroscopy or the use of light to be able to make these kinds of measurements. And the Barben oxygen analyzer is, people refer to it as O2 fluorescence or a luminescence. I'm trying to underline here. Pen doesn't want to write all of a sudden. A luminescence-based technology. It's try this. See what went on with my pen here. There we go. So it's based on light. It's going to actually use a beam of light to interrogate a sample and determine how much oxygen is there. And I'll talk a bit more about the fundamentals of that optical piece on the next slide. Some of the key features it has is it allows us to measure oxygen concentrations in gases or in liquid phase. And so we can use the same technology for doing a boiler feed water application as, let's say, a vapor recovery unit application. Got this great little touchscreen HMI, allows us to interact with the analyzer. Fast responding. And so for process control applications or applications where we want to see, hey, have I suddenly got some oxygen ingress into the system? It can be really useful. It's also very poison resistant. We can use this technology in streams that have, say, high concentrations of H2S, high concentrations of CO2, things that might potentially damage or completely incapacitate some other analyzer technologies. It's got great detection limit and ranges. It can measure down to single digit parts per million. So typical detection limits around 1 ppm in the gas phase, around 1 part per billion in the liquid phase. So we can get to very low levels of oxygen in gases and liquids. And this makes it very useful in applications like trace level oxygen in flares, O2 detection in streams that contain hydrocarbons, in nitrogen headers or tank blanketing applications. And talk about tank blanketing when we get into the applications section. Oxygen detection in liquids such as methanol and ethanol. We've even had clients use it to detect how much dissolved oxygen there is in liquid propane. And so it allows us to do a lot of measurements in different applications. This can make it difficult sometimes to know, well, is it the right technology for my application? Because rather than us being able to market this in a very application specific way, we really have to talk to you kind of a lot about, well, this is what the sensor can do, and then review the application to see if it's one where it is appropriate. But it has a very wide range of applicability. Like many analyzers for doing certain applications, we may have to build a little sample system around it. So this is one of the sample systems we've used in a gas phase application. But, oftentimes an analyzer is only as good as the sample you can deliver to it. And so it may require some stream conditioning before we actually get that sample over to the analyzer. So the methodology is based on something that we refer to as fluorescence quenching. So you can think about the word quenching. We talk about quenching a flame or something like that. We're talking about getting rid of some of the energy, pulling the energy away. And this is what happens in fluorescence quenching. We send a beam of light down a fiber optic. The beam that we send out, pick up a blue pen here. We use a blue LED or a blue light. We send a beam down a fiber optic. The beam of light hits on a surface that has a specific chemical doped into it. It's a ruthenium chloride surface. Ruthenium complex. It's a hydrocarbon ruthenium complex. Ruthenium's one of the rare earth metals. This chemical has a unique property that when blue light hits it, it glows red. It gives off red light. So the blue light hits it and it gives off red light, which goes back up the fiber optic. And we can have a detector there. I'll draw a little highball. And we can watch to see how much red light gets generated. We refer to the blue light as the excitation spectrum. It's the thing that excites the ruthenium complex and makes it have extra energy. The ruthenium complex has this emission spectrum. It gives off red light. And when oxygen touches that surface, it actually takes some of the energy that's in the ruthenium complex away, and it quenches the emission. It basically says, an oxygen molecule is out here, it comes in and it touches the surface, and instead of getting this big peak, all of a sudden I can't draw red on top of red. Like when the oxygen touches it, takes some of the energy away, and now we don't get as much red light coming back. So the ruthenium complex is there to create the fluorescence. When oxygen touches that ruthenium complex, takes some of the energy away and quenches the fluorescence or makes it smaller. So when we're used to have the analytics part of this work, we basically monitor, well, how much fluorescence am I getting back? It turns out that not only does the intensity of the light drop when oxygen touches it, but because it takes a little while for that whole energy transfer thing to go on, if we, instead of using a constant light source, use an AC modulated light source, so the brightness is going up and down, what happens is, as oxygen touches it, it shifts the waves back and forth. So the more oxygen that is there, it shifts the light that's coming back. And by looking at how much phase shift there is, we can again use that to determine what the oxygen concentration is. Oops, picking up pens again. So that phase shift is going to help us to know how much oxygen is there. Using the change in phase is useful because it makes it not so dependent on, well, how bright was the blue source to begin with? It helps us to deal with drift. And so gives us a much more stable measurement to actually use the phase shift piece. So the analyzer itself comes with a lot of features. From a hardware perspective, it comes in a packaged device that can be class 1, zone 1, class 1 div 2. We can get an ATEX zone 1 version. And so we have this, essentially this explosion-proof box that houses the spectrometer. We have a full touchscreen front display that we can access all of the settings for the analyzer through the touchscreen without opening the box. We have a place to bring in, of course, electrical connections and our fiber optic connection going out. So in this case, we see the fiber optic connection over here, and it's wherever that fiber is touching, that's where we can do the oxygen measurement. While we use things like this in process applications, medical researchers use a very similar technology because they can put a thin, tiny fiber optic right inside of an individual cell and use it to map concentrations of chemicals like oxygen inside the cell. So the analyzer comes packaged for appropriate electrical area classifications, has a full user interface, wide temperature range it can operate under, so it's suitable for indoor and outdoor installations. In some climates, not outdoor in Canada, but so typically in Canada, we'll put it inside of at least a temperature controlled enclosure. Some of the advantages of this technology is, as I mentioned before, very long-term stability and low drift. So we can make accurate measurements down at very low concentrations, down to about 1 part per billion aqueous, 0.5 part per million in the gas phase. The measurements aren't flow rate sensitive, so we don't have to put a lot of effort into trying to make sure we've carefully controlled the flow rates over the analyzer. The measurement is very specific, so it doesn't get interference or have problems with other chemicals being present. So things like carbon dioxide, H2S, sulfur dioxide, changes in pH in liquids, changes in chloride concentration, say if we have chlorides in our water, none of those things affect the analyzer's ability to be able to measure oxygen. And so we can use it in corrosive streams that have high concentrations of, say, H2S. We can use it in aqueous streams that have contaminations like metal contamination and still get good oxygen measurements. Like as I mentioned, it has hazardous area approvals, and it doesn't need a lot of sample conditionings. A lot of oxygen analyzers, if they get, for example, if you take the oxygen analyzer that's measuring parts per million and expose it to air, it'll have a very difficult time getting down to reading low concentrations again. This one responds extremely quickly to large changes in concentration. In fact, I used to run it with a sensor in a T, pull the sensor out, expose it to room air. The detector is completely saturated with oxygen, put it back in the T fitting, and within a minute or two, we'd be down to reading parts per million again. Similarly, some oxygen analyzers, for example, some of the things like tunable diode lasers, If you happen to get any liquids carryover and it gets on the optics, it really causes the analyzer to have potentially long-term difficulties with measurement again. It's going to require a full maintenance. Again, I used to take that sensor out of that tea, dip it into a glass of water, shake it off, touch it against my shirt, put it back into the tea. Within a few minutes, it's back to reading moisture or oxygen again. So it's a very insensitive to, like I say, contaminations, to things getting on the sensor, can often just be cleaned off again. It's not sensitive to excursions outside of its range. The other nice thing about it is that if it does fail, if the surface coating gets damaged, it usually fails high. So it says, you have too much oxygen. So some of the other sensors, when they die out, they fail low. And so you think that you're running under safe conditions, but you're actually not. So a typical gas phase installation may include, is probably going to include things like, I'm just going to zoom on this flow panel for a second. There'll usually be flow meters there to control flow rate to the cell, calibration flow rates, low point drains or bypasses if necessary. But it's a fairly simple sample conditioning panel. We've got sort of a sample of one sort of sitting over here. There's the Barben OXYvisor. Oops, in the corner. Can't draw when it's like that. See the Barben OXYvisor in one corner of the cabinet. Again, we've got some flow meters, some filtration, and because it was for Canada, it's all sit inside of a small heated enclosure. On the natural gas processing side, there's a lot of places where we will potentially be interested in putting in an oxygen measurement. Because of the fact that it impacts corrosion, we may want to put oxygen measurements in over near the wellhead before compression. So measure oxygen at compressor inlets. Very common to want to get an oxygen measurement at compressor outlet. That oxygen measurement lets us know, did I develop a leak in my compressor? If I've got upstream leaks through the compressor or I've got leaks in the compressor, I'm going to end up mixing oxygen with my natural gas. Oxygen mixed with natural gas obviously is a combustible mixture. And so I've created now an explosion risk, but I've also potentially created problems for some of my upstream processing units, especially on that gas sweetening side. So we generally want to try to make sure if we're going into something like an amine unit, we don't have any excess oxygen there. And so we want to know, am I making sure I'm not getting oxygen into my system from the compression side, excuse me, because if it gets into that amine unit, it's going to cause problems with fouling, with heat stable salt formation, etc. We've also usually got a specification on our sales gas. So we want to have an oxygen measurement and say, am I meeting specification when I get out to producing sales? We'll often put in vapor recovery units at gas processing facilities, at refineries, at crude oil batteries, any place where we are having hydrocarbons present in tankage. And so if I have big vessels like condensate stabilizer vessels, or I have tanks where I'm, say, storing crude oil, it's very common for us to take the vapor, the gases that come off the top of those tanks, and recompress it again and use it for some other application. It might be that it's going back into a gas processing facility for producing more natural gas, We might use that vapor that's coming off as a fuel gas. In some cases, we will blanket the tank with something like nitrogen to try to make sure we don't have a combustible mixture up there. So in all of those applications, we end up wanting to know, well, am I letting any oxygen get in as well? Because again, we want to know because it's corrosive and it's flammable. So almost any tank blanketing application or storage application, there's a potential for looking for oxygen in that overhead gas that may be going to a vapor recovery unit. Specifically, when we look at some other technologies, things like electrochemical cells can commonly get poisoned by carbon dioxide, by CO or by H2S, and when they do, they will stop responding. And so as a result, if the sensor has become poisoned, we'll end up in a situation where even though we've got excess oxygen in the system, we don't know it because those sensors will fail low. Other technologies like paramagnetic oxygen analyzers, tunable diode lasers don't have that poisoning issue, but they often don't have very low detection limits. Typically, a paramagnetic oxygen analyzer might be 100 part per million detection limit. Same with a tunable diode laser. The ability to use this fluorescence technology down to low levels like 1 or 2 parts per million lets us detect leaks sooner. It's also less expensive than the tunable diode laser technology. Carbon sequestration is very important these days. Everybody likes to talk about carbon dioxide and greenhouse gas emissions. And one of the ways that we are looking at that, addressing that from the oil and gas industry is to capture the carbon. So we do that often by running the gas over something like an amine unit. So again, going back to what I said on previous slides, if we're going to do carbon sequestration, what we'll often do is have some source of carbon dioxide gas, have a pump or a compressor to pressurize it. Again, we don't want to let oxygen get in at that compression stage, and then run that over an amine unit, absorb the carbon dioxide, and then re-inject that carbon dioxide back under the ground. It's important we don't inject oxygen back under the ground as well. The places we do these injections into, all these underground caverns and things like that, there's bacteria there that are generally what are called anaerobic bacteria. They don't want oxygen. When they get oxygen, they start to make a lot more nasty chemicals. And so we like to try to keep our injection wells with not having excess oxygen in there. So again, it becomes important because we need to protect the amine unit from oxygen. And we also don't want to inject oxygen back down into these underground caverns. Acid gas re-injection has a lot of advantages because it's a very scalable technology. We can make it really big. When we talk about things like H2S, it's less expensive than building a sulfur recovery plant, and it emits less to the atmosphere. It gives us a way to reduce greenhouse gas emissions, and it has fairly low energy requirements compared to some of the other ways to try to reduce CO2. Easier to permit here in Alberta as well. And so the Barben oxygen analyzers, again, are especially useful here because they don't get poisoned by H2S and CO2. They can handle liquid carryover in case we have problems with hitting dew points at the compressor. And it allows us to measure the oxygen in both the inlet compression stages, and after the amine unit. So again, if we kind of look at the process that's involved in here, we'll usually start out with some sour gas, perhaps it has H2S in it. We produce sweet gas. This might be natural gas. We take the acid gas that was made during that sweetening. We have to compress it. So again, we want to know there's not too much oxygen in here, because when we compress it, if we get things condensing as we do, it's a wet stream, we'll have corrosion. We'll have to dehydrate that gas as we compress it. That dehydrator doesn't want to see oxygen either. And then we pump and compress that up and push it by pipeline and put it to the injection well. There's over 25 major acid gas reinjection projects going on in Alberta right now. And all of these have to be concerned, what's going to be the impact on me if I have oxygen? Because it's going to affect it can affect my compression stages, my sweetening stages, my dehydration stages, and the place that we're pushing that oxygen back down into. So again, we have the same issues, reliability on some of the other technologies like electrochems, and the fact that we can measure at very low levels with the Barben. It's a very advantageous way to measure low levels, which tells us sooner that we have a leak in our compression stages. So like I say, carbon capture is a big deal right now. The whole world is looking at, everybody talks about how are we going to reduce greenhouse gas emissions? And while we look at alternative technologies like solar and wind, we have to recognize that 30 years ago, around 84% of all of our energy came from hydrocarbons. We spent $3 trillion trying to transition away from using hydrocarbons, let's say. And in 2022, 82% of all our energy came from hydrocarbons. We really haven't changed that very much. So if we are going to look at trying to address carbon, we're going to have to look at, well, there are ways that we can capture it and sequester it. And that's what this whole carbon capture, utilization, and storage is about. Allows us to do greenhouse gas reduction. It allows us to use carbon dioxide as a means to repressurize reservoirs and actually improve oil recovery, let us get more oil from the same well, which has energy efficiencies associated with it as well. It's a very established technology. There was just a news release at a power plant in Saskatchewan that has one of the largest carbon capture facilities in the world there. The carbon they captured at that power gen facility was the equivalent of taking 1 million cars off the road. And so, these are available technologies we can use. We can push this back down into depleted large reservoirs, and these reservoirs are known proven traps. And so we can use this technology as a means to do CO2 sequestration, but it's going to require that we make appropriate measurements along the way. And so although we're talking about oxygen right now, one of the things that Insight's involved in is we're looking at a number of applications for also putting mass spectrometers on some of these carbon capture facilities, so you can look at the full chemical composition of all the chemicals you're capturing and putting those reservoirs as well. Another place that oxygen measurement is extremely important. Again, this is going back onto this green energy side of things. You'll hear a lot of people talk about, use the phrase of renewable natural gas. And this is natural gas that's produced from some kind of a fermentation or digestion kind of process, but then is used in the same way as we typically use natural gas. Or I suppose it could be used to make hydrogen as well. But the important thing here is that this is methane that's being produced from a renewable means, often by digesters of things like fertilizer or manure, other kinds of chemical wastes, or it can be landfills where they have just, if we go to a local garbage dump, all the hydrocarbons that are underground are slowly decomposing and they produce methane over time. And so we're beginning to use this as a source of natural gas that doesn't require drilling wells. It's big in Europe. It's becoming big in the US. These are low pressure gas production though. That when we get natural gas from underground, it's at very high pressures. When we get it from these digester facilities, it's at low pressures. So for us to put it into a pipeline, we're going to have to put compressors in and pressurize this stuff up. And so we have to look at how much oxygen is coming out with the actual gas that we're producing and how much is there after compression. And so we want to make sure that we meet the pipeline specifications to prevent corrosion. So again, the Barben is advantageous here because there's often other bioproducts, especially H2S, CO2 that comes from these fermenters, doesn't attack the sensor, it's very low maintenance. These facilities don't produce a lot of gas, so we have to have a cost-effective and low maintenance solution. We'll also mention, I kind of wanted to focus this presentation on gas phase applications, but as I mentioned at the beginning, we can use this to do oxygen concentrations in liquids as well. And so a common place for these is any place where people are using some kind of a steam boiler. So whether it's up in Fort McMurray and they're doing steam assisted gravity drainage, or if they're using steam to drive a turbine, they always want to be sure that that feed water has very low levels of oxygen in it, often down as low as in the parts per billion range. And they use special chemical injection to get rid of any excess oxygen in there, because the dissolved oxygen, especially in high temperature water or high temperature steam, is very corrosive and it can attack the piping, cause leaks. So it's critical that we monitor dissolved oxygen when we're running a high pressure steam boiler. It's a scaling problem. It causes more corrosion, builds up scale, reduces heat transfer, eventually can cause the pipes to start to leak. Even low levels of it can be very damaging. Like I say, we're talking about people being concerned down in, the 10 part per billion and less range. So again, advantages of Barben brings this: very reliable, no moving parts, very precise and robust measurement down in that low ppb range, and no moving parts in this. There's almost no maintenance that's done on these. So I'm just going to give a big list of a whole bunch of applications here. Anybody who's come to our presentations before knows, we'll usually send you an email out shortly after this with a copy of all the slides. So although I spoke about a lot of the applications, there's also additional applications there on this slide. And that's going to get me wrapped up. We're going to finish up a little bit before 1, which is great. So again, Insight, while a lot of people know of us for the JP3 measurements and a bunch of the work that we do in gas plants, we represent a full line of products that allows us to do measurements in both the gas and the liquid phase. And so I'd like to give you an idea of all the products that we carry. I think our next webinar actually in February is going to be on the JP3s. And pen stopped writing there for a second. And then the XREL mass spectrometer, I think was going to be our webinar in March. It'll be March 16, I think. And Jaden, was it Feb 16 for this one? Jaden's probably not listening. All right, there he's probably handling the link inside us. Yeah.
Sorry.
Was it Feb
Which one
16?
were you asking?
Was it Feb 16 for the JP3?
23rd.
23rd. And the XREL one that we're going to do is going to have, this is going to have a big focus on, again, on carbon capture. But we've just recently been doing a project for this also on helium. People may have heard that helium's in a real shortage, so a lot of people are looking at helium plants. Things like mass spectrometers are really good for purity type applications. From a capabilities perspective, I like to just show some of the jobs that we've integrated. We'll build everything from composite samplers through to another composite sampler on pipeline, through an analyzer sample systems, automated grab sampling panels, full shelter integration for analyzers, PLC automation. We're very open to looking at projects. We're pretty good at knowing what's in our wheelhouse and what we're good at doing. We love to bid those kind of jobs. And if we can't do it, or we don't sell a product that's going to do it, we also are good at knowing, well, we can't necessarily do that job for you, but I know who can, and we'll refer you to those people. So with that, I'm going to be happy to take any questions you guys might have. I will just mention at the end, if you would like to get in any more information, you can contact Lisa. Lisa's on this webinar here, or myself. So I'll give you both our numbers and our phone and our emails there. And I do also want to mention Canadian School of Hydrocarbon Measurements is coming up on March 21st and 22nd. And Insight's promoting that we're going to do a full one-day introduction to sample systems course and training downtown Calgary, hosting at the Marriott Hotel. So if you want any information about the training course, we advertise on LinkedIn and on our website, or reach out to Lisa or myself. And that's going to wrap me up for today.